Okay, so today I'm going to talk about computer graphics, which is actually located in the chapter 10 of the textbook. We have a computer graphics course named and coded as CSE 461. It's the fourth year selective course. Today in this lecture, I'm going to talk about the scope of computer graphics, what computer graphics is, what is 3D operations, what is modeling and rendering, ray tracing, scanline rendering, what are the lighting equations, and how the animation, computer animation is done. Also, there are 2D versus 3D graphics. For example, this is a 2D graphics, right? A triangle is a 2D graphics. On the other hand, when you have a box image, it is considered as a 3D graphics because the model is 3D. Actually, the image is 2D. My screen is two-dimensional, so the image is two-dimensional. Can you close the door? So this triangle is last person should close the door. He doesn't know it, so you should do it. He doesn't know it. Same thing that I talked at the beginning of the course. If there are too many people on the street and one person is dying, nobody cares. So no problem. So we will be talking about computer graphics for the rest of the day. Let me introduce two-dimensional graphics and three-dimensional graphics again. On a two-dimensional screen, this is a two-dimensional screen. There's an X and Y. But I can display three-dimensional objects or two-dimensional objects. In three-dimensional objects, we call it three-dimensional graphics, 3D graphics. Actually, the screen is two-dimensional. But yet, since the model is three-dimensional, we call it as three-dimensional graphics. So computer graphics deals with geometric modeling. So this is an artificial scene with cones, with donuts, with the teapot, and with the lights and the windows. So in order to create an artificial image, you need to model the objects on the scene. So that is called as geometric modeling. You need to model, for example, the window with the length and the orientation and the size and the type and etc. Then using that model with the certain algorithms, you achieve the resulting image through lighting equations, through rendering operation. Through rendering operation, you create the image after the model. Sometimes this teapot is very famous, and that famous teapot is drawn first in the University of Utah, in the Utah computer graphics group. For example, this is a cube, right? Is this cube of this form? Is this the front face or is this the front face? For example, this same cube image, this is the wireframe. The same wireframe image can have two different forms. So depending on how you eliminate back lines, the object is perceived better. So on this teapot, for example, back lines are not drawn. So once you are drawing the teapot, you need to eliminate back faces. And the question is, what is at the back? What does it mean? What is back and what is front in a computer image? Because I have two-dimensional plane here. This is X and that is Y. Yet I see it as three-dimensional image. So this is kind of a three-dimensional teapot. And since this three-dimensional teapot is perceived as, since you are intelligent from the previous lecture, remember, since you are intelligent beings, you perceive it as a teapot, as a three-dimensional object. But this is two-dimensional. It's not a picture of two-dimensional thing. It's a picture of three-dimensional object. So there are back faces, and those back faces should not be drawn on screen. So you are the person in your algorithms, you are the person who is responsible from not drawing backlines. That means you need to determine which is at the back, which is at the front by calculation. Again, in reality, there is a concept called shadows. When you have a light source and an object and a screen or some surface, this object casts a shadow on the other side. So each object has shadow. Sometimes there are multiple shadows. If you have multiple shadows, what is the cause? Multiple light sources. So the location of the shadow depends on the position of the light source, etc. So those must be calculated. Those must be calculated, and computer graphics does that. That is not very hard. There are more harder things. For example, if the light source is a light source like that, which is area light source, what is the special kind of the shadow? The shadow boundaries are not sharp. We call them soft shadows. So creating soft shadows require a lot of thinking, because it is not only single light source. It is not parallel light source like solar light source, where the shadows are very sharp. We consider it as tiny little small light sources, like 64 different light sources close to each other, and we calculate those small light sources shadows one after another, and we add them up. If we add them up, then we end up with soft shadows. Thanks. You guys can catch up later from the video. Next, what is this? This is the world. Is this the world, or is this a sphere? It's actually a sphere with a picture of world on top of it. When I'm drawing this, I don't need to model the world. All I have is a sphere and the map. So this is a sphere. So I can map for example, a Turkish flag on it. So that means I have a sphere with Turkish flag wrapped around it. So we call it as texture mapping. It is actually the picture of the world, not the model of the world, but we can set it so that it wraps around a sphere and draw it on screen. So we call it as texture mapping. It doesn't happen all the time with the spheres. When you have a street in, for example, a computer game. This is a computer game, that's the street. There are buildings on the side of the road, and each building has a face, and those faces have very good details. Do I generate those details in the game? No, they are pictures. Those pictures are stuck on the face of those cubes or boxes. Boxes represent buildings. So I stick images of the real life buildings on boxes so that a box look like a building. Do you understand? So, for example, in computer games, graphics cards are responsible for performing those operations. But the thing is, somebody has to program it. It doesn't happen by itself. We say graphics card is responsible for it, yes, but somebody is programming. So that is the job of computer graphics. Sometimes we have complex geometries like the helicopter here, like a car. When you are drawing the car, it has a door and window and front glass, windshield, tires. So there are thousands of pieces. Those pieces must be put together in a data structure, maybe in three data structures. So different data structures must be put together to construct a complex image. That kind of complex geometry and modeling that geometry, for example, if it is going to be an interactive editing graphics, you can open this door. When you open this door, the rest of the car should stay intact. So it can be opened and closed in the model. Therefore, you need to define the connection points and joints in between, like a simple robotics problem. So that is the topic of computer graphics, dealing with complex geometries and complex objects. Second, remember Snell's law. Gelen açı, gelen ışık, this is normal. Gelen ışık, kırılan ışık değil mi? This is Ni, this is Ns, this is again Ni. So we have Snell's law. So there is angle of theta I and theta S. Remember that. So you have been solving questions all along for the past years. So using that equation, I can calculate how transparent objects looks like, how water looks like, how the fish in an artificial pond should be drawn, how the atmospheric effects in artificial animations can be emulated. So that is called as calculation of transparency. Therefore, I can simulate glass. For example, I can have glass lenses. I can have glass balls. I can have glass balls where I can see behind as upside down, because I'm calculating transparency effects by following the path of the light and drawing what is necessary on screen after the calculation. This is an interesting, again, University of Utah teapot. The model is teapot, the famous teapot model. Here we see that there is a person on this side. Maybe it is our image. Like when you are holding a teapot, a shiny teapot, right? You are seeing yourself. So if I am going to simulate that, I need to have this kind of picture. But do I have a teapot? Answer me. No. Thanks for answering. No, because I don't have the teapot. The teapot is on the computer. One question was, when I have a circle on the computer, how am I going to store that circle in the computer memory? The answer was, store the origin and radius. When you store the origin and radius, that's a circle. So in the computer memory. When I have a teapot in computer memory, do I have it in real life? No. But I want my image as if I have it. How am I going to do it? Because teapot doesn't exist. This could be a dragon. So we all know that dragons do not exist. Or an animal that is an extinct, for example, a dinosaur. A dinosaur, and on the eye of the dinosaur, I see myself. So do I need a dinosaur to take that shot? No, because there is no dinosaur available. So I have a dinosaur model. I have my vesicle image, right? I have my photograph. So using my photograph and dinosaur model, I can simulate the effect that my image is shining on dinosaur's eye or on teapot. So that is called as environment mapping. That is environment mapping. Maps, similar to texture mapping, maps an image on an object as if the image is surrounding or across the model. So teapot doesn't exist, but I create an image as if I am on the other side. This is extremely important when you are generating when you are launching this is the new car that we are making, right? Sorry for the drawing. It is much better, actually. So assume that I am taking an animation movie showing the Tog car driving in Sultanahmet, right? So that's an animation. But when the car is driving through Sultanahmet, since the car is so shiny on the windshield and on the body, in the animation, in the film animation, realistic animation, I should see the surrounding Sultanahmet Cami in Ayasofya and the trees on the car because it is so shiny. But the car doesn't exist. I need the movie. My boss, the president, wants it. So how am I going to make the movie? The answer is I take a video by following the path in Sultanahmet, same route with a car, with my car, take the surrounding image, take the outside, take the video of Ayasofya and the trees, etc., in the same path. Using that video with the same technique, I can compute the reflections on the car, which doesn't exist yet. So if I make the correct computations, I can make the appearance of the artificial car so that when it is passing through Ayasofya, the image of the Ayasofya minaret will be visible on the car's body. Actually, the car doesn't exist because I passed through that route with my car, took the video, and I stick to that video on the body of the model. Okay, this is what environment mapping is, and environment mapping can be done on videos as well. So computer graphics is very famous in computer games, and computer game technologies and the industry is quite significant. You can make a lot of money by writing and working in computer game companies. The level of computer graphics necessary for creating good computer games is quite significant. The techniques are relatively different in computer games because speed is important, accuracy is less important. So fast generation of usually fake graphics is acceptable because if user likes it, then it is correct. So for example, when you need a smog, when you need fog, for example, here, there is fog here. When you want to make this fog with an algorithm, how are you going to do it? You don't make physical simulations of the fog, because when you want to make a physical simulation of the fog, the particles are moving, etc., which is very difficult. So what you do is make an image, superposition, stick that figure on top of the previous image. Now users see it as a fog, so no problem, because it is fast. So that kind of tricks and speed improvements are used in computer games so that you can enjoy fast-moving graphics rather than 100% correct animation. Another money-making topic in computer graphics is the medical applications. So whether you have tomographical images, whether you have ultrasound images, there is medical data coming from the scanning devices, from tomography or magnetic resonance imaging units and ultrasound, etc. At the end, the data must be visualized, shown to doctor, and doctor will say, aha, let's cut this part out. And probably they will take more money than you. That may not be true in coming years. The important thing is they look at the image and decide whether you have cancer or not by visualization. With good visualization technique, you can help doctors to understand the cases better, solve problems better, or furthermore, those data can be analyzed by artificial intelligence that you learned in the previous hour to detect where is the sick part. Is there a problem or not? Is there a cancer or not? So the success rate of algorithms are in these years are passing the doctor's performance. So performance of algorithms for medical applications, signal processing applications, are increasingly surpassing doctors' performances, especially poor doctors' performances. During operations, during ameliyat operations, doctors, surgeons can be supported with computer graphics applications so that they can see inside of the patient in real time. You can combine the information during the operation that is received from the external sensors like ultrasound or MR or whatever, or the previously generated data, so that doctor will see inside the human body or make certain decisions based on what was wrong with the patient. So medical applications of the computer graphics is seriously important. And in production, in design of mechanical, physical, electronical systems, computer graphics is quite significant because as you are designing it, you need to see it. Therefore, modeling phases, visualizing phases, computer-aided design applications require extensive amount of computer graphics programming. This is a chip. This is a transistor, for example, a transistor. So designing of circuit of graphics. Furthermore, biotechnology, DNA sequencing, astronomy, radio astronomy, chemistry, biology, sometimes mathematics, require certain tasks called as scientific visualization. Scientific visualization helps scientists to understand things better and solve life's existing problems, solve nature underlying issues, and develop theories. So this, for example, these distant galaxies are not visible by telescope, not visible by naked eye, not visible by anything. They can only be visible after processing and colorizing radio telescope data, organizing data, and putting them on the screen. Then you will say, aha, there is a galaxy. Actually, that image is computer generated. Okay. Lastly, the animation industry is improving every day. With the advent of augmented reality and virtual reality, industry is shifting through three-dimensional synthetic environments. As you remember, recently Facebook had a different company. What was the name? Meta. In the Meta, they are going to work on meta worlds. In future, the environments like social media will be virtual worlds where you can interact with your senses in three-dimensional, plus sound, vision, sound, and probably extra additional senses that we cannot think of yet, like smell and touch. Touch is also tested years before. There are cases there are examples where you simulate certain fields of touch with the gloves, etc. They're also working on putting some transceivers at the back of your head so that you can feel certain pulses, punches after processing with electrical signals fed to your brain. So films and animation plus virtual worlds for entertainment and human interaction is quite significant topic in computer graphics. A famous question that comes from students. There is a topic work area called image processing and computer vision. So we ask, what are you doing? I am onto computer vision. Okay. What are you doing? I am doing image processing. These are relatively older topics where they mostly deal with image enhancement, feature extraction, and pattern recognition. When you talk about 3D model extraction, more like computer vision. Okay? So that requires you to have photographs or video at the beginning. So photograph of a real object is taken and then processed. That is what we call image processing. And for that purpose, we use a lot of mathematics and Fourier transforms, and there are electrical and electronics engineer departments, people working on that topic as well, or mathematicians, to improve image, for example, to sharpen the image, to colorize the image, or to squeeze the image, etc. But to detect whether there is a house and tower here, and the house has how many floors this house has, for example, that answering that kind of intelligent question is the topic of computer vision. And computer vision is therefore quite important for industrial manufacturing, where you monitor the objects in production and process them, locate them and process them with the help of the camera, along with the robotics. So computer vision and robotics go together in industrial manufacturing. Also, for example, a couple of days ago, I saw a machine in the video. I saw a machine that goes in the livestock cow milk factory with the cows. They automatically take milk from the cows. A robotic device goes by itself, detects cows back, approaches, milks the cow, and pulls itself back. So moves to the next cow. Nobody is interfering. So it is all by 3D model extraction, computer vision, etc. So I showed the video to one of my friends who is doing that kind of business. He has a farm, and he said the machine also gives electrical jolt, electrical pulse to cow, so that the pulse after milking, the cow goes away with the shock, electrical shock, the slight electrical shock. Otherwise, he said cows doesn't move away from the robot. So it is all connected. What is computer graphics then? Computer graphics does not have photographs, does not have real life objects. Computer graphics create what is unavailable. Okay? You have image, and when you go to three-dimensional model, this is computer vision. But when you have three-dimensional model and you want to create an image, this is computer graphics. So they are in different directions. They are usually related, but works in different directions. You have model, you want to go to image. You have image, or you want to go to model. The first one is image processing and computer vision. Second one is computer graphics. These are the examples from computer vision and image processing. For example, detecting edges of the objects. This is the original. This is a better image. We call it as sharpening. Derivatives in two-dimensional space. When you use derivatives in two-dimensional space and adjust it new pixels, compute new pixels based on that is called as sharpening. Or if you take values where derivative is bigger than certain predefined value, then you get an edge map, for example. Processing, where the changes are significant. When the changes are significant, they become boundaries. So that is, for example, used to detect images, detect objects in the image with the boundaries. Graphics is cool. I like to see what I'm doing. Graphics is interesting. It includes physics, mathematics, algorithms, architecture, gaming, human factors. It is combination of a lot of different issues. And recently, artificial intelligence is also going into computer graphics. It is also it also includes a lot of fun. You can enjoy it while you are doing it. This is from the Pixar's first film. And one of my friends actually worked in production of this game in 1996, I think. In Toy Story.
Toy Story 1. It's Toy Story 1.
Either 1995 or 1996. The guy got his PhD from our school in the United States and the same lab in 1994 and joined to Pixar. And he was responsible for making this figure. This is the last thing I am going to show you, and I will continue next week. When you are seeing certain things, seeing is believing. If you see something, you perceive it. So it actually happens by a light source. Light source illuminates objects, and certain light comes back to your eyes. So if you understand this process, and if you can simulate what is happening, if you can calculate what is happening, that means you can fake the computer eyes so that when you see it, okay, it's a picture. Or if it is in stereographics with the helmet, you may believe it. You may believe that it is there. Okay, I think it's good for today. If you have any questions, I can take it.